Hi, I'm Po-Han Chen, and today I will be presenting our work, 3DSA, Multi-View 3D Human Pose Estimation with 3D Space Attention Mechanisms. Our contributions are summarized as follows. We proposed the 3D Space Attention module, which addresses the drawbacks of the existing multi-view 3D human pose estimation methods and validates its effectiveness on existing voxel-based methods. We introduced a 3D space subdivision algorithm to reduce the computational complexity of the module. By incorporating our space attention module into existing voxel-based methods, both models achieve state-of-the-art results on the panoptic benchmark, demonstrating the effectiveness of this attention. Comparison between our method and the existing voxel-based method. The primary distinction is that A. The existing method simply projects heat maps into 3D space. B. We enhance feature volumes using space attention, maintaining 3D information, and emphasizing critical regions within the feature volume. Here is the overview of network architecture, which can divide into 3 stages. A. Given the multi-view image as input, the backbone network predicted both the heat maps and the space attention scores for each view. Each heat map is projected to a 3D space, which is physically shared but independent for each view, constructing the feature volume. The space attention scores for each view are assigned to the different regions in the shared 3D space. B. By performing an element-wise multiplication of the raw feature volume with the space attention scores, we produce a feature volume infused with spatial attention. Subsequently, this attention-enhanced feature volume is fed into 3D CNNs to locate the per-person proposal. C. A more detailed feature volume corresponding to the proposal was generated. By calculating the spatial relationship between the proposal and the feature volume, space attention scores for the proposal were sampled from the attention in 3D space. Finally, the human pose was estimated. The 3D space subdivision algorithm is crucial to the implementation of our space attention module. Computational challenges arise when directly predicting the significance of each voxel in the feature volume. We utilize a 3D space subdivision algorithm to partition the feature volume into separate regions, with the voxels in each region being treated as a group. Here is the detailed architecture of space attention module. It is a straightforward and lightweight design, which uses a simple convolutional block followed by global average pooling, and the sigmoid activation function to estimate the space attention scores of the corresponding image. We evaluate our model on the CMU panoptic, campus and shelf datasets. In the campus and shelf datasets, we use percentage of correct parts to evaluate our model. In the panoptic datasets, we use average precision and mean per joint position error to evaluate our model. Here is our result on the panoptic datasets. As illustrated in table, by incorporating the space attention module with 2 voxel-based methods, voxel pose and faster voxel pose, our model achieves 94.2% and 94.22% on the most strict evaluation metric AP25. Remarkably, both methods achieve much lower MPJPE with values of 13.98 and 14.55, outperforming the tempo and achieving the SOTA records. This demonstrates the effectiveness of our space attention module. The quantitative evaluation results on shelf and campus datasets are presented in table. Our proposed method remains competitive on both datasets. The performance of space attention is not as outstanding on panoptic datasets, and we believe this is related to the heat map-based input. Since the heat map lacks image information, the model is hard to determine the importance of different regions in 3D space from the heat map. By comparing the results in table, the direct prediction of all voxels does not result in significant improvements in performance. We can see that the finer the subdivision of the 3D space, the model's accuracy and precision improve correspondingly. However, the model's performance tends to converge after subdividing into 10 by 10 by 3 regions. The result demonstrates the critical importance of the space subdivision algorithm within the space attention module. The table demonstrates that incorporating the space attention module into the voxel-based approach resulted in a slight increase in the model's complexity. In this work, we focus on comparing our method with existing voxel-based methods. Regarding the model, we eventually selected voxel pose with 10 by 10 by 3 space attention module. Max increased by 1.32% and parameters by 0.74% when compared to the voxel pose model. We compared our method with existing 3D pose methods. The table shows that the feature volume representation is diminished with fewer camera views, leading to a drop in accuracy. To further validate the impact of different inputs on the space attention module, we conducted experiments on the panoptic dataset. As shown in table, although the space attention with heat map-based input shows an improvement compared to the baseline model, it is noticeably inferior to the space attention with image-based input. We consider that this disparity occurs because heat maps lack spatial and depth information in comparison to images. We provide the space attention visualization results on panoptic datasets. Observing the spatial distribution of attention in 3D space, most key attention areas are focused where people are present. This result aligns with our hypothesis, confirming that the space attention mechanism discriminates the importance of different regions in the feature volume based on visibility.